Now let's talk about the rigid rotator Hamiltonian, and in particular, how to find the eigenenergies. So remember from our previous discussion, the operator that we're trying to find the eigenvalues of is the Hamiltonian here, which is 1 over 2i times the angular momentum operator squared. So 1 over 2i times L squared. The solutions to this eigenvalue equation are typically written as the symbol y, right? And in functional notation or in a derivative notation, you get this thing over here, right? So you have minus h bar squared over 2i, and then times the whole thing is 1 over sine theta times dd theta of sine theta dd theta plus 1 over sine squared theta d squared d phi squared. Okay, and this is being applied to the function y, and we are searching for a solution to the equation where this operator acting on y gives us E, so some undetermined energy times y. Okay, and the first step we're going to do is to simplify the whole thing a little bit by first multiplying both sides by (2y) over minus, h bar squared times sine squared theta. And then we're going to furthermore try to collect all of the terms on the left-hand side. So we'll multiply both sides by this constant and then try to move everything over to the left-hand side so this is equal to 0. Okay, and next, just so we don't have to keep writing the same constant over and over again, we're going to define a new constant called beta. And then we can directly replace this to get a slightly simpler form. Okay, and now we have something we can start trying to solve. What you can notice is that if you look at this in two different pieces, the left two terms here only depend on theta, right? So there's only theta. So these are functions of theta only, whereas this last term inside of here only depends on phi. Okay, so what that means is that this total operator now is a sum of one theta dependent operator and one phi dependent operator. What that means is that we can solve this using separation of variables. So what we're going to do is to assume that we can write the solutions y as a product of a theta only function and a phi only function. And we're going to write them like this. Okay, so where this symbol here is capital theta, so this is capital theta of theta, and this symbol here is capital phi, so this is capital phi of phi. So now we just take this ansatz, this product ansatz, and plug it back into the eigenvalue equation that we had up here. All right, next we can make use of the fact that this first mini operator here only acts on theta, and the second one only acts on phi. And so for the first term here, we can pull the phi-dependent function out in front. And similarly, for the second term, we can pull the theta-dependent function out front here. And these are both equal to 0. Okay, and the next step, just to try to separate these out, is to divide the whole thing by y again. So divide the whole thing by phi of phi times theta of theta. So notice when you look at the first term, here this phi of phi that's sitting out front isn't doing anything. And so when you divide out this part, in this first term, the phi will cancel. And what you get back is this. And this can't be simplified any further because what you have is an operator acting on this thing, and so you can't simply divide this out. And you get a really similar thing happening with the second term, right? Where now, because this theta isn't interacting with the operator at all, when you divide this second term by theta, these things just cancel out. Okay, so now let's take a look. So what we have here now are two different functions or two different variables added together. So you have this function here and this other function of theta. Okay, so you add up a function of theta and a function of phi, and you get 0. Okay, so you get a constant. So you have a function of theta is equal to the negative of a function of phi. The only way that this can be possible is if both of these terms are equal to some other constant. And in this case, that constant will be the negative of each other. So in other words, the only way that this can be true, that you can add up a function of theta and a function of phi and always get 0, is if this term on the left is equal to some constant we're going to call m squared, and the term on the right is equal to the negative of that constant, so minus m squared. Okay, and this is something we've seen several times now, so this greatly simplifies the problem because now instead of having a two-dimensional differential equation, we have two independent differential equations. You'll see in a moment why we call these m squared rather than just calling them m or something like that. All right, so let's start by looking at the problem that was highlighted in green. So this is the phi dependent term. Okay, so if we rewrite this by moving the phi over to the right side, we get this. So now this is telling you that the second derivative of the phi function is equal to minus m squared times the original function. And this should already look familiar. This is a problem that we've dealt with over and over again, and we should be able to guess what the solutions are pretty much immediately. That phi will take the form of a times sine m phi plus b times cosine m phi. But for reasons that will become clearer in a minute, it's actually simpler to deal with a related way to write this in terms of the Euler relation. Okay, so we're going to work with that. Okay, so just by looking at this, you can immediately see that if you take the second derivative of both the left hand side of the equation or the right hand side of the equation, then you should get minus m squared. Okay, but this is only the first part of the problem. This tells us the general form for the solutions, but it doesn't tell us what values of m are allowed. And the values of m that are allowed are just as important as the form for the solution. So to figure out what values of m are allowed, the next thing we need to use are the boundary conditions. All right, and to come up with the boundary conditions for this, we should think a little bit again about the spherical coordinate system. All right, and so phi is the angle that any point, that this point in green, for example, makes with the x-axis. All right, and so if what you have is let's say you have a function, all right, we notice that this is an angle that goes from 0 to 2 pi. And in particular, if we take this phi and we go around the whole circle, so we add 2 pi to this angle, we should get back to the original place, right? So if we take this green dot and we add 2 pi, which means we go all the way around the circle, we get back to the original place. So what this means is that in spherical coordinate systems, any function of r, theta, and phi shouldn't change if you add 2 pi to phi. Because adding 2 pi to phi doesn't change x, y, or z, and if this has to correspond to some function in Cartesian coordinates, then this periodicity needs to be satisfied. Okay? And this defines the boundary conditions that we can use to fix the value of m. So if we plug this in, so this means that phi of little phi is equal to value of big phi at phi plus 2 pi. We can simplify the terms on the right a little bit by writing it as Alright, and now because of the way this looks, the only way that these two things can be equal is if everything in front of the im phi in this term is the same as everything in front of the im phi in this term. So what that means is that c has to be equal to c times e to the I 2 pi m. And the only way for that to be true is if e to the I 2 pi m is equal to 1. And similarly, we're looking at the other term. The only way that this term can be equal to this term is if e to the minus I 2 pi m is equal to 1. And now if we remember the Euler relation for the complex exponential, then this tells us that both cosine of 2 pi m has to be 1, and sine of 2 pi m must be 0. And this will be true only in cases where m is an integer, meaning it can be 0, plus or minus 1, plus or minus 2, etc. Okay, so then we can bind this to say that big phi now gets a subscript m, right? Because we know something about the eigenstate, and so now we can label it with something useful. And this will be, so am here will just be some normalization constant times e to the I m phi, where m is 0, plus or minus 1, plus or minus 2, and so on. So it can be positive and negative from 0 to infinity, any number, any integer at all. Okay, and I'll leave it as an exercise for you to show that the normalized versions of these ends up being what you get with am is equal to 1 over root pi. And now that we know what the phi dependence of this problem looks like, we can take a look at the theta dependence. So the first thing we can do is rewrite this by combining all terms on the left side again. All right, now let's pay attention to something special here. So this m squared is known, and we know what the values of this are. Okay, so m can be any integer, which means that m squared can be any integer squared, basically. Okay, but m isn't necessarily what we care about. What we care about is is the energy, which is inside of this beta term, right? So beta includes the energy. Okay, so what that means is that if we want to know the energy, we're basically going to have to deal with this separately for different values of m. Okay, and the solution to this equation ends up giving you what are known as the Legendre polynomials. And the associated Legendre polynomials. These are special polynomials that arise in particular differential equations, very similar to the Hermite polynomials that arose in the harmonic oscillator problem. And just like for the harmonic oscillator problem, we're not going to explicitly derive these polynomials or any of their relations. The book does a pretty good job of motivating these things, and so I highly recommend that you do look through those. But for our purposes in this class, we can just use the results of the Legendre polynomials without having to derive too much of it, or really any of it, ourselves. Okay, so no matter how you solve this now, the solutions for this end up telling you that this beta has possible eigenvalues of j and j plus 1, for j being an integer from 0, 1, 2, and so on. Okay, but remember that we originally defined beta to be equal to 2ie over h bar squared. And so what this implies then is that the energies will get a symbol j, right? So there's a quantum number in the energies again, and this is just equal to h bar squared over 2i times j plus 1, for j equals 0, 1, 2, and so on. Okay, and this is sometimes simplified by writing this as b times j plus 1. Okay, so this b is known as the rotational constant. And this depends on the moment of inertia of the molecule, and so it will be a function or be a property of the molecule itself. And the other important property that comes out of solving this is that the energy with value j has degeneracy 2j plus 1. Okay, so what does degeneracy mean? So what this means is that there are in fact 2j plus 1 different linearly independent eigenkets that all have the same energy Ej. Okay, so this is written as G sub j is equal to 2j plus 1. Okay, so let's draw that a little bit as an energy diagram. So what that means is that you have the ground state E of 0 is just equal to 0, and the degeneracy of the 0 state is 2 times 0 plus 1, so just 1. So you just have one state. Okay, and then at E1, you put in j equals 1 to this equation here, then you should have that this is equal to 2 times b. And if you put j equals 1 into the formula for the degeneracy, then you should get that this is equal to 3. So g of 1 is 3. So that means that at the energy 2b, you have 3 independent solutions. And if we go up to E2 now, so E2, if we plug in here, this is 2 plus 1 is 3 times 2 is 6, so we have 6b. And now we plug j equals 2 into g of j, and this will give us 5. So there are 5 linearly independent rotational states that all have the energy 6b. All right, so now this actually might already look kind of familiar, right? Because you have this march from a single state and then a triple and then 5 together. And so you might think this looks vaguely familiar in terms of the structure of the periodic table. And it turns out that this is not an accident, and we will definitely talk about this in later classes. So this tells you the eigenspectrum of the rotational Hamiltonian. And now in the next lectures, we'll learn about the selection rules, and we'll use these to predict what the spectra would look like for pure rotational spectra and also for mixed rotational and vibrational spectra.